All right, onward into chapter 7, which is about impulse, momentum, and collisions. And I promise this chapter will not be nearly as long and have as many different ideas in it as chapter 6. Chapter 6 is really like two chapters combined into one. Chapter 7 is more like a normal chapter. It has some new concepts in it, but I don't think you'll find it nearly as difficult as chapter 6. All right, let's start by watching a YouTube video, and this is of a baseball running into a metal wall or a metal plate horizontally, and it shows the process in slow motion. Here's the ball coming in from the right, hasn't hit the wall yet. The wall pushes on it. The ball deforms quite a bit if you watch it in slow motion, and then it rebounds off to the right again. Okay. Here's another video of a golf ball hitting a wall similarly. It's not really going to give us any more information, but I thought it was such an entertaining video. Let's watch it. It's amazing what you see a golf ball do when it's in slow motion. It turns into almost a pancake and then really deforms a lot as time goes on after the collision. There it is, almost as flat as a pancake. But the point of all this is the wall is exerting a force to the right on these things as they're colliding with the wall, and that force goes to zero after they stop touching the wall. So what I want to do now is draw a graph, just a rough qualitative graph of the wall force on the ball as a function of time. Let's just take the simple case of the baseball where it wasn't so crazy in terms of how it was deforming. And it seems like to me, if I asked you to draw it, this would be a pretty reasonable guess for what the wall force is as a function of time. The wall force, originally when the ball isn't in contact with the wall, the force on it is zero. At a certain point the contact begins, and when the ball has just deformed a tiny little bit, the force on it's really small, but the force gets bigger and bigger when the ball is maximally compressed. That's when the maximum force is exerted on it. And then as time goes on, the force gets smaller and smaller as the ball decompresses, and then finally it loses contact with the wall. That seems like a reasonable qualitative guess for what the force of the wall as a function of time is. Now, the effect of the force acting on the ball for that period of time is that it changes the velocity of the ball, or we could think of it as changing the state of motion of the ball. And I want to ask another question about this graph, which is qualitatively, how might we change the graph, draw a different graph, so that the velocity change of the ball is even greater? In other words, how could I alter this graph to make it so the ball goes even faster in the final state? And there are usually two answers people give, and both of them are reasonable. One is that I could make the contact with the wall last for the same period of time, but I could actually make the maximum force much greater. That would be like if the ball compressed even more, and so it had a greater maximum force. That would certainly increase its velocity to the right after the collision even more. Another way to do it is to say, well, I don't want the maximum force to be any bigger than it was in the original case. I could just make the collision last for a longer period of time. And so if we do that, we would have a greater impact on the final velocity of the ball than in the original case. So it looks like in both these cases, by doing those alterations, we've increased the area that's under the curve, the area under that bell-shaped curve. And so it looks like if we want to characterize the degree to which the ball's speed is changed, or the ball's velocity is changed, really, the thing that affects it in terms of the force versus time curve is the area under that force versus time curve. Because the notion of an area under a curve is really a calculus kind of concept, we're going to think of it in a simplified kind of way. We could take that area under the bell-shaped curve and deform it while keeping the area the same into a rectangle. So we're going to imagine that the contact of the ball with the wall takes place for a time delta t, and we just make the height of that whatever it has to be to have the same area under the curve as that original curve that we drew was. And I'm showing that by this kind of pink color there. And when we do that, the height of that constant force kind of curve is the average force of this averaged over that period of time, delta t. And this suggests a definition that's going to be important for how the velocity of a ball is changed by a force acting on it. We're going to define the x component of the impulse delivered to an object or a system by a force, and we'll imagine here that the force is acting along the x direction. So the x component of the force, you can imagine in that ball case, the force of the wall on the ball was to the right. If we call that the plus x direction, then we would say that the force, the impulse delivered is the area under the fx versus t curve. That is the thing that we're under the impression is going to characterize the change in the state of motion of the ball. The bigger the area under the curve, the greater the change in the state of motion of the ball during that time period delta t. And the area under the curve, again, we could re-envision that as just delta t times the average force x component being applied. All right, here's our x component there, and we can see the SI unit for impulse. So the symbol for impulse is J. So the x component of impulse is equal to the average x force component of the force we're focusing on. That's like the wall force times delta t. And we can see the units of impulse are newtons times seconds for SI units. Or if you want to express those in terms of more fundamental units, you could write out a newton is a kilogram meter per second squared, and then simplify things, and you get kilogram meters per second is also a unit of impulse. They're two equivalent ways of expressing it. Similarly, if a force isn't necessarily acting just along the x direction, there would be a y component of the impulse and a z component of the impulse, having to do with the average y and z components of the force. So we can think of the impulse as a vector that has these x, y, and z components, and we could summarize all three of these equations just with the simple vector equation, J equals F average times delta t as a vector relationship. And again, we're thinking of the impulse as a measure of how much that force that's associated with this average that we're taking here has acted on an object over time, or the degree to which it's going to change its state of motion. Now, I've given you sort of a loose intuitive idea that it should affect the change in the state of motion of the object. The impulse affects that. But exactly how does the impulse delivered to the object change its state of motion? This is supposed to be an and, not an and. Let's figure that out, and we're going to start with really the only tool we have to work with that tells us about the state of motion of an object, and that's Newton's second law. So at every instant in time, we can imagine that ball colliding with the wall, and we're concerned with the force that the wall is exerting on the ball. At every instant of time, F net equals ma. So in the case of the ball colliding with the wall, if it's in outer space, at least there wouldn't be a gravitational force, so the net force might just be the wall force. That's true at every instant of time, all the way through the compression and decompression of the ball. If it's true at every instant of time, we can certainly average that over a period of time, maybe the period of time of the collision. And if that's true at every instant in time, then it's certainly true that the average net force is equal to the mass times the average acceleration. And we can go back to our work that we did in Chapter 3 and express the average acceleration as just delta v over delta t. So this is an expression for F net equals ma averaged over some time interval that we pick. Usually it's the time interval of the collision of the force at the time the force is acting on the object. If I then multiply both sides of this equation by delta t, it's almost irresistible on the right-hand side to cancel out these delta t's in the numerator and denominator, and the right-hand side then just simplifies to m times delta v, which is m times v final minus v initial. Final is the velocity when the collision ends, initial is right before it starts. So that suggests another definition, we've got m times v final minus m times v initial. We're going to define m times v to be something new, which we call the momentum. And for reasons I don't know, momentum is always given the symbol p, lowercase p. So the momentum vector is equal to the mass. So this is that characterizes something with a certain mass moving with a certain velocity v. The momentum vector of that object is m times v, and that means the momentum vector has x, y, and z components, which depend on the x, y, and z components of the velocity, like this. So in terms of those, we can re-express this in terms of, well, the left-hand side, let's see, F net average times delta t, that is the impulse delivered by the net force, or the sum of all the impulses delivered by all the forces. We'll just call that the net impulse. And the net impulse is equal to mv final minus mv initial. We can write that as delta p, the change in the momentum, the change in mv. Or if this is sort of a very shorthand way of writing it, if we expand it out, then the net impulse means the average force being exerted on the object during a time interval delta t times delta t is equal to mv final minus mv initial. Just two different ways of writing it. That result is called the impulse momentum theorem, but don't let it seem too mysterious to you. It's really just a reworked version of F net equals ma. F net equals ma applies at every instant in time. This result is rather kind of a version of F net equals ma that's averaged over a period of time. So it's a different way of viewing Newton's second law. All right, let's take a break now, and you can work on problem number 1 of the impulse momentum worksheet. And I've put the statement of the impulse momentum theorem down here for your convenience. A 5-kilogram hockey puck is initially traveling on the frictionless ice with the certain x and y velocity components. Something happens to it. Maybe someone hits it with a hockey stick, and in this case, we're imagining that the force delivered by the stick, or whatever force is being applied to it, is constant over a certain period of time for 4 seconds. The force is applied to it. I'm imagining the xy plane is the plane of the ice, horizontal hockey rink or something like that. So a force with these components, constant force is applied for 4 seconds. What are the puck's final velocity x and y components? In this case, we could use our constant acceleration kinematics as long as we used the constant force to find the constant acceleration, but I don't want you to do that. I want you to try to use the impulse momentum theorem. And when we come back, we'll look at the solution together.